Okay, so let's look at some examples of stochastic processes. First of all, we'll start out with the simple random walk. Let x sub t be a random variable denoting the position at time t of a moving particle where t is equal to 0, 1, 2, and so on. So we're only concerned about the position of the particle at these discrete times. Initially, the particle is at point 0, and that means that x sub 0 equals 0. Remember, x sub t is the position, so if it starts at position 0, then x sub 0 to equal 0 is at each time t, it moves one step either to the right or to the left, or stays in the same position with probabilities p, q, and r respectively. P plus q plus r equals 1. I note parenthetically that if you know p and q, then you know r. Now, for example, at time t equals 1, I have x sub 1 equals x sub 0 plus z1, and in general I'm going to have x sub j equals x sub j minus 1 plus zj, where zj is the value of the step. The step is either 1, minus 1, or 0. Zj is the random variable denoting the movement at time j, and zj is equal to 1, minus 1, or 0, according to the movement to the right, left, or stay at the same place. All right, let's verify this to make sure we're not confused. So my number line is here. If I'm at position, say I'm at position L, if I move to the right, that will be L plus 1. So that means that z is equal to 1. And I move to the left, that's L minus 1. That means z is equal to minus 1. Now the index on z is not the location. The index on z is the time step. So if I'm at state L at time step j, and zj equals 1, then I'll move to the right. If I'm at state L at time step j, and I move one step to the right, then zj equals minus 1. So that's our description of random walk. Now, simple random walk has p equals q equals 1/2. And then, of course, you know what r is as a result. All right, now, what about these z's? These z's are the steps. These different steps, z1, z2, and so on, are independent. Now, that has a mathematical definition and identically distributed. Now, identically distributed, we know this because we've explicitly given the distribution. I could write my distribution specification this way. Zj is equal to 1 with probability p, minus 1 with probability q, and 0 with probability r. That's the distribution. Now, independent means that the probability that zj is equal to, I have to give some value, let's say a, given zk equals b, is equal to the probability that zj equals a when j is unequal to k. I spoke about this in a previous video. The value of zk gives me no information about the value of zj. So if you were to simulate this with a computer, the z's would be generated by independent random numbers. So there's an example given here. In particular, if zi represents the number of liters of petrol sold by a petrol station during the ith week, then xn would be the total number of liters sold during the first n weeks. This may not be a very good example because you can't really sell a negative number of petrol liters. But the point is that the z's are the steps, and the x is the cumulative result of all steps together. So that says z are steps, and then x is the cumulative sum. That's the point of this example. Now remember that the stochastic process is a sequence of random variables where the random variables are indexed by a time variable. So here we have a sequence of random variables. Xn is called the general random walk process. So this random walk process uses discrete times, and it has discrete steps. So it's both discrete in the time variable and in the value that it can take. Next example is the Wiener process. Now the Wiener process can be considered as the continuous limit of a random walk. If you take a random walk and take the time steps smaller and smaller, and instead of taking steps of size 1, you take steps of much smaller size, then you get a Wiener process. So let me denote that over here. Wiener process is the limit of random walk when the time step dt is made smaller and smaller, and I can call it the space step, I can call it dx, is also made smaller and smaller. One way of visualizing this is if you take a random walk like this, the random walk will look something like it's going to go around and go like this, right? And it'll go randomly and something like this. And you zoom out so that the space step and the time step look very small. Right. If you zoom out, what's it going to look like? Well, you won't see these jagged steps. What you'll see is something that moves around very much. It's going to be a very rough curve, something like this. Okay, this is just one sample path, right? You'll generate many sample paths like this, but the characteristics will be something like this. All right, so that's the intuition behind Wiener process. Here's the formal definition of Wiener process. A stochastic process, x sub t, where t is greater than or equal to 0. In this case, t is continuous. This is said to be a Wiener process if this process, x sub t, has stationary, independent increments. Now, how does this correspond to random walk? Well, random walk, we saw that the steps were independent. That's where the independent increments comes in. If all steps are independent, then pairs of steps are also independent. I could take 2 steps early and 2 steps late. The result of the early 2 steps is completely independent of the result of the later 2 steps. Now it's true that x3 might depend on x2, because if x2 is 1, then x3 would either be 0 or 2. On the other hand, if x2 is negative 1, then x3 would either be 0 or negative 2. So the x's are not independent. What's independent are the increments. The increments are given by, for instance, xt plus s minus xt. Now this is a random variable. This will be independent of xt prime plus s prime minus xt prime. As long as the interval t to t plus s does not intersect the interval from t prime to t prime plus s prime. So those are independent increments. And that follows from the independent steps of the random walk. Now what is stationary? The random walk is stationary because the distribution of z does not depend on n. So this follows from the random walk case because the step distribution is independent of t. So that's where point 1 comes from. What about point 2? It says for every t greater than 0, x of t is normally distributed with mean 0 and variance t. This was not clear in the original. Now how does this reflect on random walk? It turns out that random walk is very closely related to Pascal's triangle. And Pascal's triangle for a very large number of n goes to a normal distribution. Now there's a lot more that could be said about this, but I'm going to stop here. Suffice it to say that when n goes to infinity, the nth row of Pascal's triangle becomes closer and closer to the normal distribution, and the spread of values also becomes larger and larger. That corresponds to the variance. All right, so we've seen a process with discrete time, discrete space. We've seen a process with continuous time, continuous space. These are two examples of a class of stochastic processes known as Markov processes. So let's go down here to the general definition of Markov process. A Markov process is a stochastic process with the property that given the value of xt, the probability of xt plus s, where s is greater than 0, is independent of xu, u is less than t. So what's the picture here? I have my timeline, and here I have 3 times t plus s. Now s is greater than 0, and u, where u is less than t. Now x of t is going to be some value here, and x of t plus s is going to be some value here. Now we can consider the conditional probability for x of t plus s equal to some value, I can say a, given x of t equals b. The intuition is that this probability does not depend on anything that happens before time t. It only depends on where the process is at time t. I can express this by saying that the future depends only on the present. Now you can say it depends on the past, but only insofar as the past has determined the present. Now if you've taken physics and you've looked at the motion of particles, that also satisfies this property. The subsequent motion of the particle only depends on where the particle is now and how fast it's moving. It doesn't depend on what it did before. So this is a very important intuition. The future depends only on the present. You could say in a sense that the process has no memory. Once I've reached xt at time t, I don't care how it got there. That's all I need to worry about. That determines the entire future. Come to think of it, that's a good way to live one's life, but that's beyond the scope of this course. So let's go over this definition and make sure this agrees with what we're saying. The probability that x sub t is less than or equal to capital X, that's a t here, given x of t1 equals x1. Now these small x's are specific values. You know that a random variable can take different specific values. So this first random variable xt1 takes the value x1, xt2 takes the value x2, and so on. Xtn takes the value xn. And this probability, as I've written down here, is the same as the probability that xt is less than or equal to x, given that xtn is equal to xn. In other words, x at time t, conditioned on past values of the random variable x, only depends on the most recent value. So we'll be working with Markov processes quite a bit, and I hope you'll be able to develop your intuition of what this means. It's important to have a picture in your mind. So finally, let's briefly go over this classification of stochastic processes. There are different possibilities for the time step and the state space. Remember, the state space is the set of values that the random variable can assume. Remember, we talked about discrete and continuous. Discrete means it's denumerable or listable. Continuous means it's not, like the real numbers. So there's 4 possibilities for these two dimensions. Time can be discrete and state discrete. Time can be discrete, state can be continuous. Time can be continuous, state can be discrete. Time and space can both be continuous. So here are some examples of stochastic processes of these 4 types. Random walk is discrete time, discrete space. If you think of grocery prices changing, the price can be anything, so it's continuous. And if it changes weekly, that's discrete in time. You only look at prices per week. For instance, I could look at just the prices on Monday, and then I'll know the prices for the rest of the week. So that's discrete time, continuous space. Continuous time discrete space would be what's called a birth-death process. If you're looking at a population of people and you're looking at people being born and dying, when X would be the total population. We'll see birth-death processes in the next chapter. We also have continuous time, continuous state space, that's Brownian motion, or the Wiener process. And it's also what is used to model the stock market. So in this book, we'll only look at 1 and 3. The others are also very interesting and closely related, but understanding 1 and 3 very well will give you a good basis for understanding 2 and 4.